Hey, Dominic.
Hi there.
How are you doing tonight?
Good, how are you?
Good. Ah, there you are. Nice to meet you. So what are we working on tonight?
Alright. So we learned the shell method,
Okay.
and so we have both the shell method and the washer method.
And the disk method.
Right.
Okay.
And it's called the washer method in this book. I don't know.
Oh, really? They don't even refer to it as the disk method?
No.
Because a disk is a solid. In other words, if I rotated this about the x-axis, creating a solid, then I would slice this up into disks without a hole in the middle.
Right.
So
Right.
that's the only difference between a disk and a washer, is the disk doesn't have a hole
Well,
in the middle.
yeah, so I guess we did do the disk method at first before we started
Yeah.
doing.
Usually that's what people start out with, is the disk method, which is pi r squared, and then the washer method, which is r squared minus little r squared times pi. So, okay, how are you doing with your understanding of cylindrical shells?
Actually, pretty well.
Okay.
Let's see.
Notice that this shape that I drew could also be chopped up into cylindrical shells, each of
Right.
which would be parallel to the x-axis. In
Right.
other words, if we were to use cylindrical shells on this bullet, we would be integrating on the y-axis instead of the x-axis, which is what we would use if we were going to chop it up into disks. And which one you use kind of depends on the nature of the function. In other
Right. I
words,
was gonna ask you.
well, if this function is something like x cubed minus x, then it's a function that's easily defined as a function of x, and so I can integrate it along the x-axis. But if I wanted to integrate that with cylindrical shells, I would need to define it as a function of y, which is not easily done. Solving that
Right.
for x is not something easily done. So that's when you're kind of forced to use cylindrical shells or disks if it happens to be a function that can't easily be defined as a function of x or y. But I don't think I've seen a shape yet that cylindrical shells, you could use washers or disks to also do it, as long as you have a function that can be defined as either. In other words, if the function is y equal x squared, well, I can define that, x equals square root of y.
Right.
So some function like this, you could use either one, since you can define it as either a function of x or a function of y.
Mm-hmm. Okay. Well, let's see.
Do you have some problems that you'd like to try to do?
Yeah. Okay, so we have a problem where there's a function y equals sine x, and then another function y equals cosine x, and then in between 0 and pi over 4.
Okay, so here's pi over 4, their intersection. It's where they're equal to one another. And they want to take this region right here.
Right, and so we want to revolve it around y equals -1.
Okay.
So that's going to be, I guess, a washer.
Yeah, let me think about this for a second. If you haven't done these for a while, you kind of got to get back in the frame of mind of doing them. Okay, so we're going to, if we were to revolve that around the x-axis, it would be relatively easy. The radius is going to be the difference between, we would have to use washers. Revolving it around the line y equal -1. Okay, so the radius is, the inside radius is going to be sine x, the outside sine x plus 1. The outside radius is going to be cosine x plus 1.
Right.
So we're going to go from 0 to pi over 4, and it's pi times big R squared minus little r squared dx. So far, so good?
Yep.
Okay, so this becomes pi times big R is cosine x plus 1 squared minus sine x plus 1 squared dx. Yeah, you know, it's prompting me to shut off my webcam, so I'm going to do that just because it, yeah, that turns off yours also. Yeah, this GoToMeeting is very, very CPU intensive. You better not have a whole lot of stuff running on in the background. So, okay, let's see. You know how to, are you supposed to manually integrate this, or are you supposed to stick it into your computer and come up with an answer?
Well, yeah, it's supposed to be manually.
Okay. Let's do it. So
yes.
the first step is probably squaring it out.
You may actually, I mean, I understand that we get an answer, but I guess it's not a big deal if we don't go all the way through that.
Okay, you tell me where you're comfortable stopping, because we certainly don't want to spend time on doing stuff that you know how to do.
Yeah.
I'm not sure that this is completely trivial.
Yeah.
Integrating cosine squared of x requires you to use the double angle. So, in other words, integrating this part, this part, this part, and this part is easy enough. The ones actually cancel. But integrating cosine squared and sine squared require you to use that trig identity. There's no really easy way to integrate this. Just cosine squared x?
I think maybe even the case that that they let you leave it like that, because this is a book problem.
Ah, okay. Okay.
So,
we end up turning that into 1 plus cosine of 2x over 2. And then that becomes relatively easy to integrate because I can figure out the cosine of 2 theta. That's just sine of 2 theta divided by 2. So these are very easy to integrate. Integrating cosine squared of theta is a whole different story. In fact, you might not even covered that yet. I bet you haven't, because that's usually covered after doing volumes of solids of revolution. All right, so you want to go on?
Yeah.
Okay.
So there's another one here.
Okay.
One function is
Still there, Dominic, or did I lose audio?
yeah. One of the functions is y squared equals x, and then the other function is y or x equals 2y.
Okay.
Yeah.
X equal y squared is a parabola, sideways parabola, if you remember your conics. And x equal 2y is, that's y equal x over 2, so that's a slope of 1/2. So it's something like that.
Yeah. And then it's the revolving it around the y-axis.
Okay. These are both defined as functions of y. So this is a function of y, and this is a function of y. Even though we could define them as functions of x, fairly easy, we're not going to want to in this case, because by the time we rotate that about the y-axis, we're going to want to break that up into washers that are parallel to the x-axis and perpendicular to the y-axis, meaning we're going to integrate along the y-axis. After this solid is formed, it will look something like this. Okay, so again, we're going to integrate. In order to find the limits of integration, what do?
You can just set them equal to each other.
Right. So I've got 2y equal y squared. So y squared minus 2y equals 0. Y times y minus 2 equals 0. Their intersection points are 0, which we can see, and y 2. Don't really care where their x intersection point is. I care about the y value, because I'm going to integrate from 0 to 2, and it's going to be pi. What's the rest of it?
Let's see. And then it's going to be, it's right minus left? Is that what?
Yes. In other words, think of it as the outside radius minus the inside radius.
So,
Okay? In other words, the outside radius is going to be the function x equal 2y. So since this is the outside radius squared minus the inside radius squared, dy, then that turns into,
so it's 2y squared minus y squared.
okay, so 2y squared is 4y squared minus y squared squared
Y to the fourth.
dy. Now this one, you can just use the straight power rule to integrate this. You're good with both integrating that and evaluating it from 0 to 2?
Yeah.
Okay. Let's go on.
Okay.
Notice, before we go on, this could be done with cylindrical shells. You see how?
All right, let me think.
This is a good case because this is a problem that you can do with either one because both of these functions can be defined as functions of x.
Right.
If you did it with cylindrical shells, the skinny part of the cylindrical shell is going to be perpendicular to the x-axis, right, meaning you would be integrating along the x-axis.
Yeah, so it'd be, the radius would be x in this case.
Yes. And the height of the cylindrical shell would be y.
Or would it be the radius is 2y and then the height is y squared?
Okay, let's look at cylindrical shells. What I like to use to illustrate cylindrical shells is a dollar bill wrapped around. I was going to show you in the camera and I just realized my camera's off, but if you can picture a dollar bill being the cylindrical shell, and it's going to, the skinny part of the dollar bill is going to be perpendicular to the x-axis. And we're going to start with a very, very tight radius at the center, and then gradually our radius is going to get bigger and bigger as we build the cylindrical shells out in the direction of plus and minus x. So in order to figure out the volume of each cylindrical shell, we want 2 pi r times the radius. Hold on a second. Let me think about this one more time. Let's see. The volume of each cylindrical shell is the area of the dollar bill, which is the height of it, which is the y measurement, and the radius is x. So it's 2 pi r times x. No, I'm sorry, 2 pi x times the height, which is f of x. So if we were going to do this with cylindrical shells, we would want to go from 0 and let's see, if I define these as functions of y, I got y, or functions of x, excuse me. I got y equal x over 2, and I got y equal square root of x. Let's see, this one is this one. This one is this one here. So the height of each cylindrical shell is going to be square root of x it's just going to be not f of x, but the the top function minus the bottom function, which in this case is square root of x minus x over 2. So that's the height of each cylindrical shell. You take the 2 pi out, and the radius is just x. And then it would be dx. And the intersection point where these meet are x over 2 equals square root of x, x squared over 4 equals x. So when x is 2, so it's the same intersection point on the x-axis. So I believe I have this right. Does that look right to you? If I was doing this by cylindrical shells?
Yeah.
Okay.
Is the intersect 2 or?
Oh, it's 4. Very good. Very good. Now, one of the things that's interesting about doing cylindrical shells is you only integrate from 0 to 4. You don't integrate from minus 4 to
Right.
4, which can be a little puzzling to get at first.
Yeah. Right.
So, in other words, you integrate from the center out to the edge, not from the left edge to the right edge.
Yeah. It's only the original area equation.
Yes.
Area between the
Basically, yes, yes. Yeah, cylindrical shells are taught differently in different books. I've got a couple calculus books that teach it a bit differently. One actually tries to get you to imagine the shell, and the other merely tries to get you to imagine a rectangular region that's going to rotate 360 degrees about that axis. In other words, if I'm using rectangular shells here, what one of my books would do would be to draw a rectangle in there and rotate that rectangle 360 degrees about the y-axis. And the thickness, or the thinness rather, of this rectangle is that dimension right there, so that becomes the dx.
Yeah, it actually does mention dx and thickness.
Yes, for sure. Notice that in this particular case where we could use either discs, or rather washers, or cylindrical shells, they always integrate along different axes. If the washers integrate along the y-axis, the shells are going to integrate along the x-axis. This case we could use either one because I can define the function as either a function of x or a function of y. In some cases you can't do that, and then you would have to choose one method over the other, whichever one is suitable to the way the function was given to you.
Okay.
Okay.
Okay. Another question I had here actually doesn't involve the I guess volume, but it does have to do with area.
Okay.
So when you're using symmetry,
Okay.
to find the area, help me to understand how determining if a function is odd or even determines whether the negative area cancels out with the positive area and stuff like that. And how do you tell if a function is odd or even?
Okay. A function is, I kind of use this as my standard because this has an even exponent. This is an even function.
Okay.
Now, the official definition of an even function is f of minus x must equal f of x. Notice that if I plug in minus x here, I get the same function.
Okay.
I get y equal x squared. The definition of an odd function, and what I use for my odd function is y equal x cubed because it has an odd exponent. And the definition of an odd function is f of minus x equals minus f of x. The even function has symmetry about the y-axis. It is reflected about the y-axis. The odd function has symmetry about the origin.
Okay. Yep.
And by being symmetric about the origin, it basically means that you can flip this about the y-axis, flip it again about the x-axis, and you've got this bottom half of this curve. Functions that are even are cosine, y equal cosine of x. Notice that y equal cosine of x is symmetrical about the y-axis.
Okay. Yep.
Sine x is odd because it is symmetrical about the origin. So that's my lecture on odd-even functions. Now, let's talk about finding area by using symmetry. Do you have a specific problem?
Yeah.
Okay.
So it's all right. The integral from -4 to 4, and x to the 6th power times sine of 4x to the 5th.
4x to the 5th?
Yep. Then
Like that?
The 5th is inside the parentheses.
Okay, so it's sine to the 5th of 4x. Okay.
It's on the x though. The 5th. Yeah.
Okay, so the 5 only applies to the x.
Right.
Okay.
So. Okay.
Okay, if we try to determine whether this is odd or even, well, the product, x to the 6th is even, obviously, and the sine function is odd, although I don't know that sine of x to the 5th is necessarily odd. So in terms of using symmetry on this, I wouldn't right off hand know whether this was symmetrical or not. This is actually a pretty difficult integral to do. You have to use integration by parts, which I assume you haven't had yet.
No.
And not only do you have to use integration by parts, but you have to do 5 iterations of it. So this is going to be one where they would not have you do this manually. They're going to have you put this in a calculator. So
What they had what they had us do was say, so f of x equals that function, x to the sixth sine. And then after that they said they had us do f to the negative x equals negative x to the sixth sine for negative x to the fifth.
Okay, so they're saying it's odd. Okay. In other words, they're saying this function, so you're telling me that if we plug in minus x, we're going to get this. Correct?
Right.
Okay, so that makes it odd. So by the fact that it's odd, it is going to look, I don't know, I tell you what, let's graph this. I use Wolfram Alpha. It's a pretty good graphing program.
Yeah.
Are you familiar with it at all?
Yeah.
So this is x to the sixth sine of 4x to the fifth. X to the sixth sine of 4x raised to the fifth.
Okay. So obviously these two areas are going to cancel out.
Right. We can see by this graph that it's symmetrical with respect to the origin. So by whatever the problem is here, going from 0 to 4 and multiplying it by 2 would give you the absolute value of the area. Yeah, I'm not. So you're going from minus 4 to 4, which is from here to here. And what are you wanting? You're wanting the area between the x-axis and this function? If I call this whole function f of x?
It doesn't say anything about that. It just says evaluate. So.
Okay, I see. So if you stick this in a calculator, you're going to get 0.
Right.
And if you want the net area, then go from 0 to 4 and multiply it by 2.
Right.
And that would give you the absolute area of the shaded section from minus 4 to 4. Or let's take this problem here. It might be a little easier to understand it if I use this. Let's go from minus 4 to 4 on this. And let's say we want the net area of that and this. Well, clearly, if we go from minus 4 to 4, this is y equal x cubed. We'll get 0 because this is negative area over here, this is positive area over there. So if we want the net area of the red shaded, I'd go from 0 to 4 and multiply it by 2, or you could go from minus 4 to 4 of the absolute value of that, which will also give you the same thing. In other words, if you take the integral of the absolute value of a function, wherever that function is under the x-axis, it basically acts like it's above the x-axis, and you get this area instead. That's the effect of putting the absolute value signs around a function, is wherever that function is negative, it makes it positive.
So why don't we go through that?
Manually doing this integration?
Well, we don't have to do that one, but...
Oh, the one that I just gave you?
Yeah.
Y equal x third to the third? Sure. That's relatively easy to integrate. So I want to integrate, and we'll do it both ways.
Okay.
Y equal x to the third dx, and if I go from minus 4 to 4, I should get 0. Well, x to the fourth over 4, evaluated from minus 4 to 4. You can see that whether I put in 4 or minus 4, I get the same thing, so this minus the bottom one has got to be 0. So instead, I'm going to go from 2 and go from 0 to 4. And now if I evaluate this from 0 to 4, I get 64 minus 0. So this is equal to 64 times 2 would be 128. I think that's right. Excuse me. X to the fourth, that's 16 squared, which is 256 divided by 4, which is 64. Yeah, no, then times 2 is 128. Okay, I think I did it right. So
when you're evaluating, that function would give an area of 0?
If I had from minus 4 to 4?
Yeah.
Yeah, here, let's do that one again, because I'll show you.
Yeah, no, I saw that, but then doing the absolute value of it gives you the positive area. So what is that called, like, doing?
Well, if you wanted to get this off of a calculator, then you would write int absolute value of x cubed, comma x, comma minus 4 to 4, and that should give you 128. If you have, I should be able to do that on Wolfram Alpha also.
Yeah.
Oops.
So that's just figuring out, the area regardless.
Okay, so this should give me 0, which it does. And now if I want the absolute value, let's see, do you know what that is on probably ABS? And then I need to put the function in. Okay, so this should give us 128. The nice thing about Wolfram Alpha is that it shows you exactly what you've typed in. In other words, if you get your parentheses wrong or something, you'll notice it when you look at the integral. But notice what it did. It just reversed what was to the left of the y-axis, where this function was normally below the x-axis. It just made it positive. Just reflected it over the x-axis, that part of it.
Yep.
Okay. What else you got?
Okay, so can we do this one right here? Integral from 0 to 3, and then absolute value of 4 minus x squared dx.
Okay. Now, if I want to do this manually, I mean, I could stick that in the computer easy enough, just like I did the x cubed. But if I want to do this manually, this is a parabola whose vertex is at 4, and it opens down.
Right. It gives a hint, break up the integral.
Right. And
is how you get a
well,
positive.
the only thing is that this we don't need the absolute value of. Oh, hold it. No, this point is 2. Excuse me. That's 2, and
Right.
we're going to 3. Right. So, in other words, they want this plus this. And yeah, and in other words, the way to do this is to go the integral of that from 0 to 2 of just 4 minus x squared. And then if you do minus the integral from 2 to 3 of 4 minus x squared, knowing that this will be a negative number, and doing minus that negative number will be the same as treating it positive. So that will essentially be the same as finding this area here.
Okay.
But when you have to do absolute values by hand, you want to go from point to point wherever it's positive and negative. In other words, if I wanted to do the absolute value of the sine function, I go from here to here, and then I would add the negative of that. In other words, go from here to here, and then I'd go from here to here if I had to do it manually.
Okay. So then you take the antiderivative of each of those pieces.
Right, let's go ahead and finish it. So this piece here becomes 4x minus, go ahead, you help me out here.
X to the third over 3.
Okay, and that's going to be evaluated from 0 to 2 minus
4x.
And what you want to be very careful about here is your parentheses and your signs. And it's minus because I know this is going to give me a negative area when I evaluate it from 2 to 3. So that's basically what I want to do right there. And just to be safe, let's put parentheses around that also. Yeah, since I know this is going to give me a negative number, then I have to subtract it in order to make it positive, essentially.
Okay.
So you're always going to subtract the area of the function that is below the x-axis. Now, to evaluate this, let's go ahead and do that. Substituting.
Is that for any problem like this, where you're breaking up the integral?
Yes, if it's absolute value and you have to do it by hand, then you have to go from the part that's positive above the x-axis, separately from the parts that are negative below the x-axis.
Okay.
Okay. This, I just substituted 2, and I got 8 minus 8/3 minus 0, because when I substitute 0, this whole thing is 0.
Yep.
And then I'm going to subtract, and this is, let's see, we have 12 minus 27/3 minus, notice all my parentheses here to keep things straight, 8
Yep.
minus 8/3.
Yep.
Okay, so let's make sure this, the right half comes out to be 5 1/3. Oh, I'm sorry, the left part, minus, and then what do we have here? We have 12 minus 9, 3 minus 5 1/3, or minus 2 1/3. So we have 5 1/3 plus 2 1/3, 7 2/3. Would be our answer.
Okay. Cool. All right. Well, I guess with our remaining minutes, we should probably go over just one more shell problem.
Okay.
Shell method problem.
Mm-hmm.
We can come up.
I've got some in my book if you like, or if you have one.
Yeah, that'd be good. And we just started learning Look too, but that's not going to be on the quiz tomorrow. So.
The shell method isn't? I didn't hear the last thing you said.
No, we just learned. We just learned work.
Ah, okay.
The,
And work can be a little tricky also.
that's not good.
Okay. Well, let's see if we can do a shell method. Here, I've got a pretty good one. And the reason it's good is because it requires you to use the shell method. Is that fine? Okay, we want to rotate this. And this function is basically looks like this. It's a lot like the sine function. And we're going to rotate it about the y-axis.
Okay.
Okay, so that after we're done, we're going to have something that looks like that.
Is contained by y equals 0.
It's contained by x equals 0, and well, it's contained. Excuse me. It's contained by the x-axis, which is y equals 0. Sorry. Yes. And this intersection point is 1. So if we were to try to use washers here, they would have to be washers that were parallel to the x-axis so that their skinny part would be dy. And that would be perfectly fine, except for the fact that we have a real difficult time defining that function as a function of y. It's very easy to define it as a function of x, but it's very hard to define it as a function of y. I wouldn't know where to begin. To solve this for x, which means that we can't use washers, because the only way you can integrate along the y-axis is if you have a function of y. You can't integrate a function of x along the y-axis. So we use our cylindrical shells, and so we're going to take the integral from 0 to 1, and it's 2 pi times, my book says f of x times g of x, or h of x, but we know that the radius, the f of x is the y, and the h of x is just x. Let me see if I can explain this by the method they use. They start with a rectangle that they're going to rotate about the y-axis, creating that cylindrical shell. Okay, so the area of that dollar bill, so to speak, after it's unfolded, if you take that dollar bill that's wrapped up as a cylindrical shell and unfold it, then this is the circumference, which is 2 pi times x, excuse me, yeah, because it's 2 pi times the radius, which is the circumference, and the radius is the distance from there to there, which is x. And then the height of this cylindrical shell is y, or x minus x cubed. So I want to take the integral of f of x, which is x minus x cubed, times x dx. And that's the setup. And then, of course, we just distribute that and integrate using the power rule. Let me, just to be perfectly clear, let me turn my camera on for a second and make sure that you're understanding what I'm saying here. What happened to my camera? I don't see it. Do you see me?
Yeah, I see you.
Okay. So in the case that we're talking about here, each cylindrical shell is going to look like this, and it's going to sit on the x-axis like in this orientation, not in this orientation. It's going to be like this. So the one at the middle is going to have a real tight radius, and as we go to the right on the x-axis, the radius gets bigger and the height changes of the shell. The height is the function. That's what y is. And the radius on the shell is the x measurement. It's the distance from here to here, and that's x. Okay. Stop sharing my camera again. It didn't like that very much. It didn't show it to me. And that's how we get the volume of each shell is the area of that rectangle that you get when you unfold the shell times its thickness. And its thickness is dx. Because I had it sitting perpendicular to the x-axis, the skinny part of the shell was dx.
Okay, I see. So the thickness is, like, yeah, very thin, right?
Yes. In other words, every time you slice up one of these volumes of solids of revolution, you have a skinny side. Whether you're using discs, washers, or shells, you have one dimension that's going to approach 0. That's what I call the skinny side. And with the cylindrical shell, it's the edge of the shell that is the skinny side. So if you took that cylindrical shell and you unfolded it, imagine taking a label off of a soup can and unfolding it. it becomes a rectangle whose length is the circumference of that shell, which in our case is 2 pi r, r being x, and the height of the cylindrical shell is this measurement here. Well, that's y, which in this case is x minus x cubed.
Yeah.
So
then
dv is actually this times that times that. So I could actually say that dv, meaning the incremental volume of each shell, is that. There's the differential equation that describes the volume of each shell.
Okay.
And then I get the total volume of all of them by integrating. Dividing both sides by, or integrating both sides like this. The left side gives me volume, the right side gives me the total volume of all the shells.
Okay. So
And again, I don't want to go from -1 to 1. I want to go from 0 to 1. Because that will actually cover all of the shells that I'm going to end up with. In other words, this object, I could make me a whole lot of paper rectangles and fold them up and construct this object from those shells. And in fact, I wish I had a box of discs, washers, and shells of varying radiuses and heights. Because then all of these three-dimensional objects I could actually put together using, a box of these things. Imagine making a sphere using quarters, nickels, pennies, and dimes. You could come close, right?
Yeah.
You'd put the quarter in the middle, the nickel next, the penny next, and then the dime. You wouldn't quite have a sphere, but you'd have the makings of a pretty good sphere. Well, if you had enough coins of varying radiuses, you could actually make a pretty nice sphere.
Mm-hmm.
Same thing with all of these objects. All right. Any last questions?
So now distribute that.
Oh, one thing I wanted to remind you of.
Distribute that x there.
Yeah, we'll do that in a second. Your Melissa, is that your mom? She paid $50, and online sessions are only $40. So you got a $10 credit towards the next one.
Okay, thanks.
Okay, just to remind you.
Yeah.
Okay. So yeah, the way we integrate, or the way we solve this integral here on the lower right, or now on the upper right, would be to distribute the x. So you have x squared minus x to the fourth. Now you can just use the power rule. So it becomes x cubed over 3 minus x to the fifth over 5, all times 2 pi. Evaluated from 0 to 1. Which is going to be 1/3 minus 1/5, which must be 2/15. So we have 2/15 is what that evaluates to times 2 pi. So 4 pi over 15 should be the answer to that. And that's what it is in my book.
Looks good.
All right, let's call it a session here.
It was a full session. We wrote the answer right at 6 o'clock.
Yes, we did. Any last questions or anything, Dominic?
Thank you very much.
Oh, sure, no problem. I love
tutoring
tutoring.
right now. No.
I love tutoring
If you have
calculus.
any question, any quick ones?
I tell you what, if some night you just need a 20 or 30-minute session, that's fine with me. They don't have to be hour-long sessions. So
Okay.
you're always welcome to call me and see if I've got a half hour open. If you don't see anything on my schedule for an hour opening, and you want a shorter session, that's fine with me. As long as I have a spot,
All of those sessions online, are those all hour-long? Or
most of them. In other words, when you go to schedule the online sessions, they're all 1-hour sessions. So if you say you wanted a 2-hour online session, just do 2 in a row.
Yeah.
And if you only want a 30-minute session, go ahead and schedule an hour-long session, and we'll just quit at the end of 30 minutes, and I'll only charge you for 30 minutes.
Okay.
Okay?
Cool. Sounds good.
All right. And you got the copy of this file? You got that email, the link?
Yep, I did.
It'll be that same link for this recording also.
Okay.
I'll just put them all on that same page. It's a private page that nobody else knows about. So they'll all be one on top of the other. The most recent one will always be nearest the top.
Okay. Sounds
Okay?
good. Yeah.
Sounds good. I'll talk to you next time, Dominic.
Okay.
You're welcome.
Take care.
Bye-bye.